you will see off to the right, you will see something that says reactions. If you click on that, Peter, then you can do a thumbs up or you can do a hand clap. And so I recommend both. And so with that, Dr. Colin West and Quantum Technologies, thank you very much, sir. And oh, by the way, please mute your microphones unless you actually have a question. And so we are going to start. Thank you very much, Colin.
Thank you. I appreciate the introduction. I appreciate the thumbs up. I'm glad that there's not a thumbs down option that you guys can take advantage of. So we'll have a guaranteed positive reaction to my talk here. I'm just going to switch here and screen share my slideshow. So you'll get just the small picture of me, I guess. I hope I got the slides up here. I'm still getting used to doing things on Zoom as well, so I hope you guys will bear with me if I'm struggling with a little bit here. This is a fun experience for me as well. And I want to say that from the outset, so I'll be talking about this is a technology, cybersecurity and policy seminar, and I'll be talking only about the first two, and really mostly just the first one. And I will totally have to leave it up to you guys to think about what the policy implications are of the things that I'm talking about here, because that's something I'm interested in, but something totally outside my area of expertise. But my goal is to chat a little bit about some technologies that are becoming available or may be available in the future to us through the magic of quantum physics, if you will, and talk about what they are capable of and the things that they are likely to change in our society, or at least technologically change, and the things that they're not, because I think I see a lot of stuff on both sides of this. A lot of people underselling the power of some of these possible quantum things, and a lot of people overselling it too. So my goal here today is mostly to try to thread the needle and represent what is real and is not, separate myth from fact as best we can. Please feel free to type questions in the chat and things as we go along. If I spot them, I'll try to answer them in situ, as it were. And if I don't see them in time, we can do questions at the end. So, what does quantum mean? Before I talk about quantum technologies, I should define my terms a little bit here. Quantum, for broad strokes purposes, for our purposes, let's assume it just means extremely small, and I really mean extremely when I say extremely small. I mean like submicroscopic. So basically, small molecules, maybe we're beginning to be able to observe quantum stuff clearly in small to medium molecules. Certainly individual atoms, certainly things that are smaller, like individual electrons, individual particles of light, like photons. That's what I think of as quantum stuff. This picture here on the right won a science photo contest a couple years ago. It's from David Nadlinger at Oxford. And it shows right there, you can just barely make it out, an individual strontium atom being held in place by a pair of electric fields. So that's the kind of thing you should think when someone tells you something is doing quantum stuff. Picture that one little pixel right there, that little dot in the middle of the atom trap. That's the kind of thing that does quantum stuff. The reason we care about this, the reason it matters that things are extremely small, is as technology and physics and science has evolved, we've been able to study the laws of physics on smaller and smaller and smaller scales. And we discovered about, gosh, we're closing in on about 100 years ago, believe it or not, that there are all kinds of rules that apply to everything in the universe, but that you only notice on the scale of really small stuff, submicroscopic stuff, which we call the laws of quantum physics. When you look at individual, I keep emphasizing individual because they need to be isolated from another. You put a bunch of atoms together and you make, say, a person. All the different quantum effects on all the different atoms that make up me are all pointed in different directions, and so they average out and basically disappear, which is why they weren't noticed until we got to the point that we could manipulate individual atoms at a time, like Dr. Nadlinger did here. But if you start playing around with individual atoms, interacting one-on-one, 2 or 3 atoms at a time, that kind of thing, that's where you see all sorts of laws of physics that you have not seen before, have not noticed before. And they give you the capability of doing all kinds of stuff you have not maybe tried to do before. First off, real quick, let me zoom in here on the picture. Just want everybody to be clear that there really is a pixel in the center of that picture here. This really is that strontium atom, one individual strontium atom being held here. I do have to say that the scale of this picture, this distance here is about 1 millimeter apparently, which means this thing is actually out of focus. It's much larger looking than it should be. You must be getting some backscatter off it that makes it look a little bit fuzzy. But the idea that we're at a stage as human beings where we can isolate one single atom, hold it in place, and then take a picture of it, I just think that's magnificent. I wanted to make sure everybody saw that. Okay, so quantum things are tiny things, and there's these new laws of quantum stuff that come into play for tiny things. And I would distill down the 3 types of things that happen at the quantum scale that are drastically different than what you see at any other scale as the following. So the first is some physical properties are truly random. Many physical properties, actually, turns out, are truly random, as far as we can tell, in the sense that there is currently no deterministic theory that predicts the properties of these things. And in some cases, we think we have strong theoretical and experimental evidence proving that there could be no deterministic theory underlying these things. Or at least if there were, we would have to sacrifice other ideas that are so dear to us about the behavior of the universe that it's sort of unthinkable. It's less weird to think that parts of nature are truly random than to accept what we'd have to accept in order to explain it otherwise. So I emphasize here not pseudo-random. Some of you guys probably know a lot about this stuff more than I do. You can ask your computer to generate a so-called random number for you, but it's not really random, right? Your computer is using an elaborate, complicated process to come up with a number, and the big picture hope is that it's elaborate enough that nobody could predict what it's going to be. So it's effectively random. But there are things that happen on a quantum scale which seem to be truly, genuinely random, totally unpredictable, regardless of how much information you know about the system ahead of time. So that's quantum weirdness number 1. Number 2 is that properties which you would think were mutually exclusive, you might even think would be definitionally mutually exclusive, are not. If you had, for example, a quantum penny, if you took a penny and you shrunk it down to the scale of a single atom or something like that, we think of a penny as having a property that's totally binary. It's either heads up or it's tails up. For a quantum penny, that's just not the case. The penny is capable of being somewhat heads up and somewhat tails up in any kind of mixture you like. Mostly heads up, but a little bit tails up, 50-50, and so on and so forth. The parenthetical is important here too. This kind of weirdness exists until you look at it directly. If you flip a quantum coin and you slap it on your hand, while you're not looking at it, it might be some mixture of heads up and tails up. Once you look, then it has to commit itself to one or the other of those states. And the easiest way to think about sort of why that should be plausible is once I've looked at it, I've interacted with it. Streams of photons from my macroscopic light bulbs have hit it, they've bounced off, they've hit my eyes. So it's become connected to all sorts of other objects and systems, which are all too big to be quantum. So we cause it to average out and pick one particular state to settle into. But there are very clever experiments people can do that allow things to interact with one another while they're not looking. And then we look only after they've interacted, and we can tell from the way that they appear after they've interacted that during the time we weren't looking, while they were interacting, they weren't just heads up or tails up. They weren't just green or blue. They weren't just going to the left or going to the right. They were doing a little bit of each. That's a powerful, totally different thing than what we expect about macroscopic objects. Quantum weirdness number 3 is that things which look like physically distinct objects, things that are spatially separated from one another, turn out to actually sometimes be part of just one underlying physical identity. And this is what's known as quantum entanglement. I'm presenting this a little bit differently maybe than some people talk about quantum entanglement, but it's the way I've come to think is best to understand entanglement. You can have 2 individual atoms, one in my lab, one in yours, one in my lab, one in Tokyo, and most of the time the atoms are totally unrelated to one another. But if they have the right kind of shared history, if we manufacture them together in my lab and then you took one of them with you and we did it the right way, they can share this property that really they are one part of one single physical system. that you cannot completely characterize one without a description of the other, which is what I mean. They're one physical entity. The way they interact with the universe fundamentally requires both of them together. They look different. We're used to, in the macroscopic world, thinking of objects as being different objects if they're spatially distinct, if you can, move your hand between them and there's no strings between them. But that turns out not to be the case at the underlying level of the universe. There really is no such thing as a distinct physical object. So you can have a physical entity, which is several physical objects, all connected up in some manner. So these are what I think of as the most profound, important weirdnesses of quantum physics, maybe the most fundamental ones. And as we talk about some of the technologies today, I'll try to point out which of these things are the ones enabling these possible technologies. I know I haven't said anything about sort of how we know these things are true or where they come from. That could take a semester or two of courses in quantum theory, but I'd be happy to address questions about that later on if folks have them. So let's move on to talking about what quantum stuff can do for our information technologies. I think there are a few categories that I would put things in here. The biggest one you've probably heard of is quantum computers. Along with that comes the possibility of quantum encryption and of quantum communication. These are the big three, I think. This first one is really the big one, and it's the one I'll primarily focus on today, but I'll say a little bit about these two towards the end. I should say also, there's a whole field of what's called quantum metrology, quantum sensing, using quantum stuff to make measurements, make sensors, which can then measure other quantum things. That's an enormous field, but it's one that's mostly of interest to physicists, and it's one that's a little bit outside my area of expertise in quantum technologies anyway. So shout out to the folks in quantum metrology. I won't be talking about you today, but we know you're going to revolutionize your field as well. So the first one, a quantum computer. What is a quantum computer? Well, quantum stuff is stuff that's on the scale of about an individual atom or so. So a quantum computer is a computer whose essential components, the components that store the information and process the information, are small enough to experience quantum effects. You probably have the cartoon picture of a regular computer in your head, that it's got a bank of switches on the inside in the form of transistors or microtransistors or microchips, things that can be ones or zeros. There's some physical thing that's storing the information, all the ones or zeros, your hard drive. There's physical chips that operate on the ones and zeros, change the data on your hard drive. All of those are made out of real world sized things, right? Small stuff, but not individual atom sized things. If, on the other hand, you made a hard drive where each 1 and 0 wasn't, a macroscopic magnetic switch or something like that, or a transistor, but was an individual atom that was either pointing this way or that way, or maybe both at the same time, then you would have built a quantum computer, one whose operations can take advantage of doing things that are only allowed in the laws of quantum physics, things that can only seem to happen to objects that are extremely small. Here's a picture of a famous quantum computer, the D-Wave computer. D-Wave is a private company that's spun out of UCB, not UC Boulder, sorry, UBC. I mean, but is a joint venture now with Google and with NASA and a number of other groups. It's one of the very famous ones of the currently existing quantum computers. All this stuff on the outside, of course, is all window dressing. This is just the shell they put there to make it look snazzy. The heart of a quantum computer like D-Wave looks something like this. There's a whole lot of non-quantum macroscopic stuff that goes on here. And then at the very heart of it, there's a little region where you could have that individual strontium atom, or this one doesn't function with individual atoms. It functions with the interactions of individual electrons, but it provides a place where submicroscopic particles can exist and interact with one another. And they're the things that form the heart and soul of the computer. And because they are at the quantum scale, they're able to do things that a regular computer cannot. Another term that's important when we talk about quantum computers is qubit. For the life of me, I don't know why we don't just write Qbit instead of Qubit. You'd think this would be pronounced Qbit. Also not to be confused with that new streaming service Quibi or whatever that's coming online now. A qubit is the quantum equivalent of a bit, so that whatever thing is a 1 or a 0 inside your computer is a bit. whatever thing that you send over the internet, when you're sending a stream of binary information, you're sending a bunch of bits. The equivalent in a quantum computer is called a qubit. So whatever thing, somebody in chat tells me, I thought I got the name of that streaming service right. That's great. The equivalent of that is a qubit. There's another question in the chat about the current state of quantum computers. I'm going to answer this one, I promise. So the thing about qubits compared to regular bits, the thing storing information in a quantum computer versus the thing storing information in a regular computer. A qubit, in a certain sense, has more informational capacity, right? A bit, by definition, is a thing that stores the smallest amount of information you can imagine. One thing or another thing and no other choices. A qubit has more capacity than that. But it's not just free extra information. There are trade-offs. They're much more fragile and they're harder to control. And I mean this in a few different ways. So fragile, meaning it's an individual atom. And remember, if that individual atom ends up interacting with too many other atoms, it loses its fundamental quantum character and loses its ability to do quantum stuff. So you really have to keep the individual atoms or the individual electron junctions isolated from too much of the rest of the outside world. And if you fail at that, even by allowing a little bit of heat to creep into your system, that kind of thing, you lose the quantumness of your qubit. It just becomes a bit and you've totally broken your quantum computer. And I say less control, this is going to come up later on too, because of that first quantum weirdness. There are things in the universe that are fundamentally random. And I guess also that second quantum weirdness, when we look at something that's doing a quantum thing, it randomly collapses in one direction to the other, commits itself to some real world looking state. That randomness can totally wipe out whatever you were trying to get your quantum system to do if you're not very careful about it, right? You might get a bank of qubits and use them to calculate some number that's the answer to some problem that's very important to you. But if you then measure those qubits the wrong way, you will cause them all to assume a random value that was totally unrelated to what you were hoping to calculate. And mercifully, that doesn't happen spontaneously with classical bits, with computer bits. There's great power here, but with great power comes what? Great fragility, I guess, in this context. It's not exactly a free trade-off. Because the key is when you eventually measure a quantum bit, when you cause it to interact with the macroscopic world, you steal its quantum character, you force it to become a regular non-quantum classical object, and then you've lost the quantumness of it. So you got to be very careful to only do that when you're ready, and you've got to orchestrate your quantum procedures to prepare you for that accordingly. I'll just flash this diagram here. Don't be intimidated by the technical stuff on here, but by a way of comparison. So a classical bit, as I said, has two values, 1 or 0. Literally, there's only two states it can be in. You can call them whatever you want, but there's only two by definition. A quantum bit has a 0 state and a 1, be anywhere in between. And it can also take on uh-oh, I see I'm having internet connection issues possibly here. Make sure I've got, let's see if I can, sorry about that. A quantum bit can also take on an additional parameter that can allow it to be not only anywhere between the 0 and 1, the top and bottom of this, but anywhere on this imaginary sphere of space in between them. So if you think about the number of possible locations someone could be on a sphere versus the number of possible locations someone can be if they're constricted to a 1 or a 0, there's literally infinitely more possibilities here. But that fundamental fragility means it's not infinitely more free information. There's a very important trade-off that keeps these things from getting out of control. So now let's talk, as a couple of you have alluded to, about areas where a quantum computer would have an advantage over a regular computer. There are quite a few, but interestingly, there are fewer than a lot of people think. There's a pretty compact list of the areas that we're aware of where a quantum computer would help. The first is quantum simulation, and with that comes some ability to do some linear algebra. This is the one that gets physicists really excited. It's very hard to get a traditional computer to simulate a quantum system. I know that's part of what I did my PhD work on. A quantum computer would be excellent at simulating another quantum system. And the basic reason is just it speaks quantum as a native. It is quantum. So it doesn't have to translate it into non-quantum stuff and manipulate it that way. It just manipulates it as a quantum system. Quantum mechanics is also a fundamentally linear theory. So if you can do quantum mechanics, you can do some problems in linear algebra on a quantum computer a little bit better. Emphasis on the word sum. Everybody gets excited when I tell them a quantum computer would be great at linear algebra, because a lot of academics know a problem that they'd like to solve and they can't because it involves inverting an enormous matrix. A quantum computer, we're not aware of ways yet for it to have an advantage over solving problems with dense matrices and things like that. It's a little faster than our best proposals for classical techniques for solving linear algebra problems with sparse matrices and things like that, which is good, but it's not a free solution to any linear system you can think of, far from it. Another area where quantum computers have a significant advantage is searching data sets, particularly unstructured, unfiltered data sets. So if you just have a whole bunch of data points and they're not in any kind of structured array or structure of any kind, finding the one which corresponds to what you're looking for can be done much faster on a quantum computer than a regular computer in principle. This is another thing that gets a lot of people excited. There are all kinds of math problems that you could solve by writing down every possible solution and then just searching the data set for the correct one. We don't do that now because it would be ridiculous to give your computer a list of every possible shape that a protein could fold into and then ask it to search every one of those shapes and find the one that corresponds to the biomolecule that you're interested in, because there'd be quadrillions, if not more, and your computer would never finish. But there are some problems like that we think a quantum computer could do by just brute forcing it with a little more finesse. Brute force is fine if you can do it really fast. And last but not least, quantum computers are excellent at finding the periods of functions, which is because they can do a thing called a quantum Fourier transform, which lets them transform things to period space and then analyze them very, very rapidly. To put that in non-technical language, they're very good at analyzing a particular property of a certain type of math problem. And human beings have been very skillful at trying to think of clever ways to use this. So there aren't a lot of problems that are deeply important about finding the hidden periods or hidden things in stuff of their own value. But there are lots of problems that clever people have discovered you can map onto a period finding problem and then have a quantum computer solve it as a period finding problem. So of course, the most famous one that a couple of you guys have alluded to is prime factorization. If you need to factor a really, really, really large number, it turns out there's a way to do that via period finding, and quantum computers are very good at period finding. So quantum computers are extremely good at factoring large numbers. I'll add one more caveat thing down here, which is almost every problem that we think a quantum computer would be better at falls into one of these three categories. There are a small handful of weird kind of black box oracle type problems that have been basically constructed for the purposes of studying quantum systems. I don't want to deny the existence of those in case any of my physicist friends end up seeing this. But none of those are problems that we think have like deep use to society. They're toy problems that we use to play with quantum computers. The real problems lie up here, and these are, as far as I'm aware, still the only sort of three areas where a quantum computer can do stuff. If you go to catalogs of quantum algorithms for quantum computers, you'll see dozens of them. I think there's at least like 60 of them on the repository that I am most familiar with. But all of them fall into, there's some elaborate version of using the quantum Fourier transform to do something that it hasn't been used for before. So this is something I think a lot of people don't realize about quantum computers. They are not sort of infinitely and all-encompassingly better than regular computers. There are a few narrow fields in which they are tremendously better. And the rest, we're still not sure. I think it's significant that it's been probably, 25 years or more now since the first algorithms in all three of these categories were proposed. And we don't have any new categories in those 25 years. So there's some reason to think these might be it. This is still a lot, but it might be it. Yeah, Peter in the chat says you don't want to watch YouTube on your quantum computer. There'd be absolutely no reason to do that. Your quantum computer will be no better at rendering 4K video than your regular computer. It'll probably be worse. So I'm talking about things being better. I have a couple technical graphs like this. They're not too bad, I promise. You probably have heard of, or maybe you've heard of, I don't know, Shor's algorithm is probably the most famous thing that a quantum computer can do. Shor's algorithm is the thing that allows a quantum computer to factor really large numbers faster than anybody else could previously conceive of. And this graph conceptualizes that. So these steeply curved lines here, this is a graph of how long it takes to factor a number versus the length of the number in bits here. So you can see as the number gets longer, this line here is the non-quantum way of doing it, and it just skyrockets, right? As I go from a you know, what are we at in log scale here? You know, a few hundred bits. As I try to approach 1,000 bits, it would take a regular computer, I'm shooting up to past 1 billion years of time to factor that. Now, this curve here, this is from a paper from 2006. This curve here was what they thought a bank of traditional computers could do in 2003. And then I love this. This line here, from this paper in 2006, mind you, was their projection of what a computer could do in 2018, assuming that Moore's law continued and computer performance continued to improve. And I think it's essentially on target. I'm not an expert in this. Somebody who knows more about the number field sieve than me can tell me, maybe we've moved this line a little bit. But look, 15 years of progress resulted in just shifting this curve to the right the tiniest bit. We still are nowhere near being able to get to 1,000 bits, factoring that in any reasonable amount of time. As far as anybody knows, there's no reason to think that's likely to change. Now, somewhat alarmingly, there's not a proof of that, but that's where we think we are. These diagonal lines are Shor's algorithm run on a quantum computer, a particular instantiation of Shor's algorithm. And the different placements of the line just corresponds to the different clock speeds of the quantum computer running it. So a really slow quantum computer, one that did things at a rate of 1 hertz, one clock cycle per second, still can outperform a classical machine by an enormous amount after you get past 1,000 qubit number. But the really interesting stuff happens if you run Shor's algorithm on a quantum computer with any kind of reasonable clock speed. Shor's algorithm running at a million clock cycles per second can do in 1 hour, maybe 1 day, let's say, what takes about 1 million years for a bank of traditional computers to do as far as factorization. And that's a megahertz. We think we probably could get to gigahertz quantum computers. This could do in a few hundred seconds what might take 1 million years to do on a traditional computer. This is the graph, the concept that got everybody really excited about quantum computers back in the day. There's at least one thing that they just crush, right? That they can do not just better, but immeasurably better, incomprehensibly better, right? A few hundred seconds versus a few million years better than regular computers. And that's really exciting. If you've got even one thing that you can do that much better, it's worth investing some time into it, I think. But as I said on the previous slide, there are only a few discrete categories where we think we have this kind of extraordinary power at our disposal in a quantum computer. By the way, I just want to point out, I've seen this graph or versions of this graph like since I was in high school. It's a very famous graph. I've probably looked at it 200 times in my life. And a couple days ago, as I was putting these slides together, I found myself looking at it and thinking, what's wrong here? Why is this a straight line? This is log scale. Why is this a straight line? It's because I've spent so much time the last few weeks looking at log linear plots of epidemic growth. That I was looking at this and expecting it to be log linear. It's log. It's log in the number of bits and log in the number of in the amount of time. So this straight line here for Shor's algorithm is saying that you can factor a number in a way that scales as about the cube of the length of the number, which is not amazing, but it's extraordinarily better than the exponential stuff going on here. So sign of the times. All graphs look log linear to me by default in this current time period. So, as was suggested, the reason you guys might be really interested, you cybersecurity folks might be really interested in the impact of Shor's algorithm, is that a lot of our current cryptography systems are based on the assumption that it's really hard to factor a really large number. That's the one-way function or versions of it that are the basis for a number of, as I understand it, the vast majority of current public key crypto systems, the stuff that protects your information when you're shopping on Amazon. Certainly it directly attacks RSA. Diffie-Hellman, you may not think of that as relying on factoring exactly, but it relies on something which is vulnerable to discrete logarithms, which turns out to map onto period finding. So that security key exchange protocol, it would also be trivially solvable by a quantum computer with sufficient resources. Lots of elliptic curve stuff, even that can be mapped onto things that can be done with a quantum computer. So this is one of the biggest reasons folks care about this. A quantum computer with a reasonable amount of resources and a reasonable clock speed would just shred a lot of our current encryption systems. And I say would because we're not there yet as far as a computer with a reasonable amount of resources. And I'll talk more about that later. But we're knocking on the door of it. And so there are lots of smart people trying to anticipate this before it happens. I promise we as physicists, we're not out to try to steal your credit card numbers. We're not building quantum computers because we think we would like to do this. It's just a side effect, but it's something that we should all talk about. The good news is, in response to this, as I said, lots of smart people have been thinking about it, and lots of smart people have discovered all kinds of post-quantum encryption protocols. Those are protocols for encryption that are designed not to be trivially solvable through quantum period finding, quantum Fourier transforms, that kind of thing. I emphasize all of these have no known quantum attack. The problem is we really don't know the capabilities of a quantum computer. So it'd be extremely difficult to prove that your particular proposed encryption scheme could not be attacked by a quantum computer. On the other hand, that's no different than where we are with our current crypto schemes, right? Nobody has a proof that RSA can't be solved by classical computers. People have been trying for decades and they haven't come up with anything, so that seems like good evidence, but there's no proof that it couldn't be solved without a quantum computer. The same will be true for these post-quantum things, and we're no worse off than we currently are. Just to flash some technical names on the screens for people who know these things, lattice-based cryptography is the most famous one that there's currently no known quantum attack on. Elliptic curve stuff, if you elevate it to the level of what are called supersingular elliptic curves, you can do supersingular elliptic curve isogeny, and this so far has proven totally intractable for quantum computers. And even just basic symmetric key crypto protocols, which are different from public key protocols, do not seem to have a lot of the same vulnerabilities to quantum computers. So it's not as though a quantum computer breaks encryption on the internet. It just changes what that has to look like. And so this is more a policy problem than a fundamental transformation of society, right? Like people need to switch over to post-quantum encryption if we think quantum attacks on RSA are around the corner. That has to happen at large scale. That has to be a smooth transition. But there's no reason to think that the post-quantum encryption world will be any different from like a game theoretic perspective of hackers versus security people than anything else. It's just a transition that we need to find our way through. Are we there yet? Jasmine's asking again. We are not there yet, and I will get more specific about this in a bit. We are a long way from there. I don't know that I have a projection of how close we are to that, but I'll try to give you some benchmarks about this. Let me start by saying a few sort of things as far as reality checks about quantum computers. Stepping aside from factoring large numbers really quick, one of the other things that quantum computers are famously really good at is searching databases. One thing that gets said about them a lot that always makes me cringe when I see it in a newspaper article is that quantum computers could search a database infinitely fast because they can try all the possibilities at once. People who say this mean well. They're thinking they've heard that a quantum bit can be both up and down or some of each. So they're thinking my quantum hard drive can be in every possible configuration at once. So I can store every possible solution to the problem on the hard drive at once. That part's actually true. But you can't try all the possibilities at once, right? Because of that third quantum weirdness thing, which is once you go to, or second quantum weirdness thing, which is once you go to interact with it, you end up making it non-quantum. So you might have a hard drive that has every possible solution to the problem stored on it in a quantum state. But if you want to read something off that hard drive, you have to make it non-quantum. And at that point, something random is going to happen, which is going to prevent you from getting access to the correct answer, even if it was there, unless you're very, very clever about how you do it. The algorithm that allows quantum computers to search faster than regular computers, oops, here comes my cat. We're having this seminar perilously close to her dinner time, so she may be making an assistant appearance on the side of the screen. The algorithm that allows quantum computers to search faster than regular computers is called Grover's algorithm, named after Love Grover. Here's a similar graph of its performance versus classical search to a rough approximation. As the size of the search space gets bigger, as I search a larger and larger database. And you can see the number of steps that it takes to search a large database in Grover's algorithm grows much more slowly. It grows with the square root of the number of things you're searching. Though there are a couple of things to point out here. First of all, this is not actually an exponential improvement like we had in the case of Shor's algorithm. It's better, but it's, you know, we're not talking the difference between millions of years and a few seconds anymore, right? We're talking about 36 years versus 6 years, right? A square root improvement. So that's significant, but it's not quite the same sort of warp your brain kind of improvement. The second thing I want to point out is, if quantum computers really did just try every possible possibility simultaneously using quantum superposition, this purple line should be flat, right? It should take just one step to perform a search, no matter the size of the database, as long as you have a large enough quantum hard drive. And that's just not the shape. And that's because that's not what quantum computers do. It can instantiate every possible solution at once. But to pick through them and put itself in a state where it can hand you the correct element that you were searching for requires a certain number of operations. And you can't get around that as far as we can tell. So the results from a quantum computer for search, for factoring, for anything that we know how to do in a quantum computer, sometimes people portray it as though they would just solve all these hard problems instantly, and that's just not right. It's especially true for problems that aren't in that quantum period finding, quantum Fourier transform category. It would do it faster, differently, but certainly not instantly. This dorky picture here is my broad strokes metaphor for why that is, why a quantum computer can't just give you the answer after considering all the possibilities instantaneously. My metaphor is very broad strokes, but I still think it's pretty good, is imagine Superman trying to look for a criminal in an apartment, in a high rise, some massive apartment building. Regular police searching for this criminal are like regular computers. They've got to knock on one door at a time. Is it the guy? No, it's not the guy. Next one. Is it the guy? No, it's not the guy, right? You just got to go one at a time. If it's totally unstructured, and that takes a long time. Searching an unstructured database takes a long time. Superman has X-ray vision, so he could hover outside the building and see through all the walls, and he could behold everybody in their apartments all at once. But just because he was seeing everybody simultaneously didn't mean he could zero in on the guy you were looking for instantaneously, right? He can take in all that information, but his brain still needs some time to sort of narrow down, okay, not the women, not the short guy, not brown hair, not blonde hair. Okay, that tall guy with red hair. I don't know why we're searching for Conan O'Brien or whoever, but you can pick out a person after a few iterations. You could see how it'd be faster. You could rule out broad swaths of the possibilities at a time if you could behold all of them at once. But to actually narrow it down, it would still take you a few steps. And that's basically big broad strokes how a quantum computer searches a database. It's better, but it's not magic. Another bit of reality check here, which will start to address the questions about where are we at with quantum computers, is to say that the quantum computers are not unambiguously better than a regular computer. It's much more accurate to just say they have different capabilities. I think of it as like, you know, if you've got a company that's full of right-brain people and you want to hire a left-brain person, like, it's not because they're better, but maybe they're bringing in a whole bunch of skill sets that nobody currently has, and maybe that augments what your overall capability is in an interesting way. So there are certainly some things that a quantum computer does manifestly better than a classical computer. A quantum computer could do anything a classical computer could do, but a lot of the stuff that a classical computer could do would be needlessly complicated to do on a quantum computer. In some sense, it might be worse at doing a lot of the things that a regular computer would do. It's not better, it's just different. As a result, they're very unlikely to displace classical computers. People talk sometimes as though we're all going to be carrying quantum iPhones in our pockets in 20, 30 years. I don't see any likelihood of that unless you expect to use the device in your pocket to factor large numbers or solve certain elliptic curve problems. If you're using your device to download stuff from YouTube, I think you're going to prefer a classical computer for that one because we've already optimized it for that. And another reason they're not going to displace classical computers is that every proposal for a quantum computer requires classical computer as part of it, right? There's a fundamental quantum thing that's storing the quantum information, but at some point you have to process that quantum information on a classical level to make it perceivable to us classical folks. So as far as I can tell, at least based on any current proposal, any quantum computer that a classical person, a human being, can use is going to include a classical computer as part of it in some fashion. So the need for people who can operate and code and develop classical computers and improve them is not going anywhere anytime soon. Over here on the right, I've got a little Venn diagram of sorts of like how the kinds of things a classical computer and a quantum computer can do, how they relate to one another. So if you imagine all possible problems that you could ask a computer to do in a finite amount of time with a finite amount of resources, some subset of those problems are interesting. They're ones that like actually might have some application and map onto things that aren't just totally random. And there's only some fraction of those that our computers can currently do in any reasonable amount of time. Somewhere within this set of interesting problems, there is also a collection of what we think are the absolute hardest interesting problems. Those are the ones that like would really tax, we know a computer just couldn't do it without billions or trillions of years. It's too bad because if we could do these, by virtue of being the hardest, they would allow us to trivially solve a lot of the other interesting problems. But we're nowhere near being able to solve those. The line for where quantum computers fall is probably here. So they can do anything a classical computer can do, not necessarily better, sometimes maybe even a little bit worse, but they could do anything a regular computer can do. They can do a decent amount of interesting problems that a classical computer cannot do easily, like factor really large numbers. They can also do some weird stuff that right now we have no idea of any use for, but that is way far away from a computer being able to do it. But to the best of our knowledge, it does not crack into this space up here. No one yet has a proposal for a quantum computing algorithm that can do these hardest, interesting problems. Maybe someone will come up with one. Been 15 or 20 years since the first quantum algorithms, and no one has. So a lot of us are growing skeptical. But at the moment, this space is untouched. So the effect of a quantum computer is meaningful, but maybe modest relative to the grand scale of all the problems you might imagine asking a computer to solve. I should emphasize, all of these are best guesses. Complexity theory, figuring out what a thing can do and proving it, is a very difficult field. Some of you probably know about this. And we can't even prove trivial statements in here, let alone statements about what a quantum computer can do. So a lot of this is conjecture. The things we know for sure is that a quantum computer can do anything a classical computer can do, although in some cases it's a little bit worse. And we know there are definitely some things that a computer can't do easily that a quantum computer can. We know there are a few things that a quantum computer can do that no classical computer could ever do, though all of those so far are uninteresting. If we have folks in the audience with some complexity theory background, think of this. I guess this is really could be anything. I'll find it problems. This could be P space. This is NP. This is NP complete, and this is P. And this thing here, the quantum computer region, we think is what we call BQP. One last wave of reality checks. The most important thing to know about quantum computers, especially if you're worried about attacks on RSA, Diffie-Hellman, things like that, are that all of these algorithms, these are software for quantum computers. We are writing this software before there is hardware that's even remotely equipped to run that software, right? We're at the stage of writing things that could run, on a large scale computer, but our computers are still, slightly above abacus level, but just barely. So whenever you see articles about what a quantum computer could do, look carefully to see if what's being described is an algorithm, which is software, a proposal of what a program that you could run on a quantum computer, or if it's hardware and software. If someone's saying they've got this program and they've run it, that's much more impressive. Very few people have run impressive quantum software yet. To give you a taste of the current benchmarks where we're at for quantum computers, Jasmine, this addresses your question directly. I think right now, a large quantum computer like IBM's quantum computer is one of the biggest ones out there in terms of how many qubits it has. It's I think the IBM one is maybe 75 qubits. I don't keep up with these benchmarks, and they change a little bit all the time, but it's of order, maybe topping out at 100 qubits. Same with D-Wave, the Google computer. Same with every instance of a quantum computer that I'm aware of, as far as any computer with any kind of multi-purpose function. A few people out there have large quantum computers that are designed with a lot of qubits, but they're not really general qubits. They're qubits that only functions qubits if the computer is doing one specific task, and that task is usually one of those weird, no one would care about this, it's just a toy problems. So I don't really count those, right? They're nowhere near having a societal effect. So, you know, because qubits have trade-offs that make them better than bits in some ways and worse than bits in others, think like a computer with 100 bits. It's not much of a computer, right? It's a great proof of principle, but it's not going to get you anywhere. Quantum computers get interesting when we hit maybe around 1,000 qubits. They get really interesting when we get to 3,000 or 10,000. Those are the projections of like where they really start doing cool stuff that might have real world impact. So we're at least a power of 10 away from that in terms of the sheer size of a computer. And the reason is qubits are fragile. Each qubit has got to be an individual isolated atom or a very precisely controlled junction where electrons can flow. And it takes this entire room worth of stuff, coolant and ancillary computers and backup systems and additional systems that do error correction just to keep 50 stable qubits, 75 stable qubits. It's an entire room for just that. You'd need at least 10 entire rooms, and they'd all have to be networked, and the quantum bits would need to be networked. We're a long way off in that sense. Another benchmark as far as factoring goes, this is one everybody cares about, right? Quantum computers would be amazing. They'd have a significant impact if we could factor large numbers with them. The largest number factored by a general purpose quantum computer right now is 21. The caveat here is that computer was specifically designed to factor 21. It was not a quantum computer that you go up to and say, will you factor some number for me? I choose 21. It was a computer whose entire architecture was physically hard-coded to factor 21. So we're a ways off of cracking a 256-bit public encryption key. Great question in the chat about how do I know that this is the current benchmark? Are there maybe countries, companies that might be far ahead and are keeping these things secret? Can't prove a negative, so I don't know. There certainly could be, but I can tell you these things, even these benchmarks, have only been achievable through massive international collaborations of physicists and engineers. The level of resources that it took to do this would be extremely hard to keep secret. So the people doing secret stuff here, unless they were several orders of magnitude smarter and more productive than the best physicists out there, and I'm not one of those, but I've met them and they're very smart and very productive. So I'd be astonished if that was humanly possible, or it should just be sucking up resources that would be missed. Someone would notice all of those salaries, all of the money being funneled into that kind of thing. That's my sense anyway. Last thing I want to say about benchmarks, you guys may have seen there was a big stir just earlier this year. Google D-Wave in particular claimed to have achieved what they call quantum supremacy, which was the first genuine instance of running a problem on a quantum computer that they felt a classical computer could never come close to running. I think this is basically true. There was some pushback for a while. I think they're basically correct that they've done this. There are a lot of sort of important caveats to keep in mind here. The most important is the thing that they claim to have done in an unimaginably faster way is a very niche quantum simulation problem that has not a lot of known application. It was a computer hardwired to do exactly that. If you're curious, the problem was, well, actually, I don't think I can explain it in a short way, and I'm running late here. So I'll let you guys ask me later if you're curious. Yes, it did it faster than we think any classical computer could by many orders of magnitude, but it was also a very small problem, a very niche problem. I think of it more as a proof of concept. There's really no direct link from the computer doing this to doing Shor's algorithm at a large scale. It was a totally different type of quantum computer. It doesn't mean we're anywhere near the factoring thing. Think of it as Scott Aronson, who is a real authority on this stuff, now at UT Austin, I think, compared it to the Wright brothers' first plane flight, which lasted maybe 9 seconds or 13 seconds or something like that. It's a long way from a 13-second, just barely more than a glide, to intercontinental flights. And that's basically where we think the gulf is between this kind of proof of principle for a machine versus deploying it at scale. All right, I better pick up the pace a little bit here to try to finish on time. I do want to say, I've been trying to say a lot of stuff that I think is downplaying some of the hype about quantum computers. It's important to point out, in 1947, this is what a state-of-the-art computer looked like. Here's Marilyn Westcott and Ruth Lichterman programming ENIAC, a vacuum tube computer that was the size of the room. 30 years later, here's Steve Jobs and Steve Wozniak and some guy drinking a Coke. Debuting the Apple II, which was enormously more powerful and enormously smaller. In between, there was a sudden dramatic change, which was the invention of transistors and later, of course, of microprocessors. Could there be something like that lurking out there that will cause a sudden dramatic increase in progress of quantum computers? Possibly. I can't foresee it, and I don't think anybody can. But very few people could have foreseen that at the age of vacuum tubes either. And it's not lost on me that our current quantum computers are the size of a room and can't do very much. Maybe 30 years is about the right amount of time. We'll see. A lot of folks are becoming a little bit skeptical because of what's happened, because you could have made this essentially the same statement about 20 years ago. But we'll see. As we've all learned from epidemics lately, when things grow exponentially, all kinds of crazy stuff can happen. And sometimes technology progresses exponentially. I'll flash this quote up here also from 1949. Although ENIAC is equipped with 18,000 vacuum tubes and weighs 30 tons, maybe in the future, computers might have only 1,000 vacuum tubes. They might weigh only 1.5 tons, right? So take my best projections about where technology will go with a grain of salt, mine and everyone else's. We're all extrapolating in a kind of linear fashion. You never know when there might be a sudden phase transition in our technologies that might sneak up on you. So it's worth having a little extra layer of preparedness if you're in a field that cares about whether RSA is about to go defunct. It's not gonna, I don't think it's gonna happen overnight, right? Somebody in a lab in Russia is not gonna announce this overnight. Could it happen in a span of 10 years instead of 30 if we get caught off guard? Maybe. I'm almost out of time here, and I need to leave time for questions. I think I will, I have a few more slides left, and I'd like to just speed through them, at least 2 of them a little bit, if that's okay. I can stick around longer for questions if you can. If anyone has questions they want to get in and they have to go at 5:30 sharp, start typing them to me and I'll try to get to them. I want to emphasize one other thing that a quantum computer can, that quantum technologies can do aside from a quantum computer, and that's just plain old quantum encryption. To be clear, you do not need a quantum computer of the type that Google or IBM or Microsoft are building to do quantum encryption. Quantum encryption is kind of happening now. It's still kind of a gimmick. When I was in grad school, there were some companies on Long Island that proudly offered to quantum encrypt your information as it was sent from Manhattan to your bank on Long Island and vice versa. I think it was a gimmick to attract rich people who wanted to be able to say they banked through quantum encryption, but they did do it. So quantum encryption should maybe more properly be called quantum key distribution, hence the stupid looking quantum picture of a key over here on the right. You crypto guys know the difference here. Basically, instead of directly encrypting your data, what the quantum thing does is allow you to generate the key, the secret number that keeps your data encrypted. And it generates it in a way that in some ways is more secure, or at least, let's say, differently secure than the quantum keys, than regular key distribution. The beauty of this is it operates on that first quantum weirdness. Nature is fundamentally random, so we can use quantum mechanics to generate a fundamentally random number, not one that's pseudo-random. It's even more deeply random and unpredictable. It's literally unpredictable as far as we can tell. It's against the laws of physics to be able to predict its value. And by using entanglement, that's that linkage between 2 distant atoms, 2 distant quantum systems, you can ensure that this totally random key is shared securely between 2 people. And last but not least, because entanglement is fragile, it can be shared securely, meaning maintaining that entanglement link requires perfect isolation of the physical system from outside influences. If there is an outside influence from an eavesdropper, it breaks the entanglement, and that shows up immediately in the quantum encryption protocol. So you can try to eavesdrop on quantum key distribution. You can try to intercept the key while it's being generated, but it's impossible to do it without physically disturbing the system. There's actually a very good physical proof of this. That said, there are attacks on quantum cryptography in the works as well. I met this guy when I was at a conference in grad school. He identifies as the world's first quantum hacker. He now runs the Quantum Hacker Lab at the University of Waterloo, and there are a couple other groups that do the same thing. Notice his awesome shirt here. The things I'd say about this is just when you read a proof that says quantum cryptography is perfectly secure, remember that the proof assumes that it's perfectly implemented. So it means that the equipment never malfunctions. Nobody ever accidentally exposes a bit that they weren't supposed to. Nobody ever accidentally leaves their side computer logged in before they start up the quantum encryption, right? So it's good, but it's not perfect in some fundamental way. Its vulnerabilities are similar to some of the ones of the other encryption things out there. In particular, a man-in-the-middle attack, somebody pretending to be Amazon to you and pretending to be you to Amazon, might, at a large scale, still be able to intercept your encryption stuff. The hardware that runs it is still vulnerable to a number of hardware attacks if your hardware isn't perfect. And the tech that runs this, like any quantum thing, depends on a classical computer doing side processing as well. So that classical computer is still vulnerable to classical attacks if it's just protected by a regular password, and someone might be able to get some kind of worm into the classical system. So quantum cryptography is really exciting, does bring some new and different types of security. Different security is good because it changes up what hackers have to do to try to access it, but don't let it be oversold to you as sort of ultimately totally impervious to stuff. It's just quite not on that level. I'm gonna skip my last two slides here unless there's questions about them. I put them in here more for completeness. It's the kind of stuff I do on a daily basis, but it's probably mostly disconnected. But I'll be happy to address broader questions about quantum communication if folks want to ask about those. So that's my talk, and I'll stop the screen share now so I can answer some questions directly. Starting with this one from Andrew. Andrew says, are there any serious ethical conversations centered around quantum computing and encryption? Yeah, totally. They are mostly happening in like philosophy and philosophy of science departments and policy departments. I think most physicists have arrived at a place of feeling technological genies are going to get out of the bottle, and it's best if that happens in broad daylight. So we'll do our research on quantum computing and how it could hack conventional encryption in broad daylight, and we'll do our research on post-quantum encryption in broad daylight, and we'll trust our institutions to manage the changes that both of those things could bring to the world. I think we're far enough along now that there's enough open source quantum simulation stuff. It would be very difficult to suppress that in any meaningful way. On the other hand, we're at a place where we're very technologically limited. So at least we don't expect to be blindsided by people running Shor's algorithm on a 3,000 qubit quantum computer anytime soon. Shannon says, do you see a need for any new standards around quantum computing other than keeping anything in broad daylight? Yeah, that's a great question. You guys are all asking things that I sort of wish I'd thought about, the policy and practical implications of these things. I am aware of a few conversations that have gone on in some sort of futurist groups around standards for quantum computing and that kind of stuff. They're very speculative because we really don't even know what a quantum computer would look like yet. There are a lot of, unlike the early stages of conventional computers, which were vacuum tubes, we have a number of different proposals of how best to instantiate quantum bits. And we're not even sure which of those are best. Some of them may be best for certain types of problems, some of them for others. So it's hard to go into the details of what kind of conventions and standards could be put in place without even knowing what exactly they would look like. It's also difficult to talk about how these things would interface with conventional computing because quantum information, quantum bits are just fundamentally physically distinct, and you always require some conversion to classical bits first. So a lot of the discussion has centered around managing that interface when a quantum computer touches your classical computing systems. I'm less aware of discussions about standards within the quantum computing itself, though it could easily be taking place outside my peripheral vision. Scott says, are you aware of any academic university working to apply quantum to the area of wireless communication? Yeah, lots of quantum communication is wireless in some sense. We did a test on this in Boulder, actually. I didn't know this until recently myself, but long ago, actually. Boulder did a test of quantum communication from the top of the physics building here to another tower elsewhere in Boulder. And apparently we had to get clearance from the city to be broadcasting stuff at that height because it technically ran afoul of aviation requirements because there's an airport in the area, that kind of thing. Photons are quantum, individual particles of light. Photons can be entangled with one another. So you can run any quantum encryption protocol, any quantum communication protocol with entangled photons, almost any. In principle, any, in practice, almost any. And if you can do it with photons, you're best off doing that via fiber optic cable. That's where you get the best transmission, but you can do it through the open air. This has even been done from satellites to the Earth by now by a couple of organizations, one in India, one in China, I think. Probably some American ones have by now as well. I used to kind of keep track of the distance record, the longest distance that we'd shared entangled qubits over, used to perform quantum encryption over, and it just started skyrocketing fast enough that I lost track of it. I figure once you can do it with a satellite, you're basically there. You know, we still have to scale it to a large number of bits and a good data rate, but the distance part is basically there. Can we do it to our spacecrafts? Voyager 2 on the outside of the solar system by now? Probably not. But other than that, we're there as far as that goes.
Fantastic. Thank you very much. I'd love to follow up with you after. Thank you. It's
my pleasure, of course. Yeah.
Intriguing. Well done. Thank you.
It's 5:30, so I won't be offended if people start logging off now, but I also don't have a ton of plans yet other than feeding my cat, who's still sitting to my left in protest here. Happy to answer other questions though, or as I said, you guys have my emails at the end of the slides, colin.west, Colin with one L, colorado.edu. I'm always happy to take questions. It's nice to have an excuse to talk quantum stuff with people.
So everybody, technology, cybersecurity, and policy. Let's please thank our speaker. You actually know how to do that now. Actions.
Lots of fan claps. Thank you.
Right,
Thank you guys very much.
And so everybody, thank you, Colin. This has been exciting. You've moved us in new directions. Students are asking really provocative questions, and I'm glad to know that RSA is not broken. I have never transmitted any money between a bank on the East Coast using quantum something or other. And so thank you very much, sir. Thank you very, very much. Okay.
My pleasure. Thank you guys for having me.
One last clap, everybody. Okay. So thank you. Thank you, Peter, going by hand. So Colin's willing to stay around for a bit longer. If you have questions, comments, or assertions, please feel free. Thank you, sir. Wonderful.
My pleasure.
Wonderful talk.